Now, in this video, we would like to talk about the concavity now. Okay, so the idea about the concavity is we have seen this before. For example, like f of x equal to x squared. Then in this case, you will see that the function of x squared basically is open upward, right? But we could actually, in math, we say that this is a concave up. Okay. Or I'm using the CCU to represent a concave up. Okay. And if g of x equal to negative x squared, then, okay, so in this case, of course, the functions of g is open down, then this one right here is the concave downward then. Okay, so then I'm using CCD, right? This is kind of like the idea about the concavity of functions. But let's see how we define the concavity then. It said that right here, a function is concave down if the rate of change is decreasing. Okay, then what is the idea about this? Okay, now let us look at our first example here. Okay, so this one, again, this graph right here is a concave downward then. Okay, now look it up. The slope of, for example, like the tangent line, okay, the slope of the secant line, maybe I say that here, between x equal to 1 and x equal to 2, okay, so it is about, again, we go up by 2 units and 1 by 1, so it is about 2, okay. Then how about the slope of the secant line between 3 and 4, okay. So in this case, you will see that this one right here, okay, so it is about 1.5, okay, over 1. Do you see that the slope, okay, the rate of change is decreasing from 2 to 1.5. So in this case, this curve right here is a concave down then, okay. On the other hand, if the rate of change is increasing, then we actually, the function is concave up, okay. Then similarly to this one right here, okay, you will see that the slope of the secant line between 1 and 2 is about 1.5. And then how about this one, okay? The rate of change or the slope of the secant line between 3 and 4 is about, we go up by 3 units and then 1 by 1. So it's about 3, okay? Do you see that the rate of change is increasing? Okay, so then this curve right here, it will be the concave up. Okay. Okay. Then to some of the function, okay, they are a point where a function change from concave up to concave down, okay, or from concave down to concave up, then we call this point inflection point. Okay. Okay. Then now, how is this relate to the calculus? Okay. Now, one thing about this is, remember, we say that, oh, if f is increasing, then f prime is positive. If f is decreasing, then f prime is negative, right? So then remember, what is rate of change? Rate of change is related to f prime, the change of a function f, right? So now we have the rate of change is decreasing. So meaning we are looking for the derivative of f prime is decreasing, isn't it? F double prime is negative. And the rate of change is increasing, meaning f double prime is positive. Okay. So then we could use the second derivative to help us to, again, talk about the concavity as well then. Okay. So graphically, concave dan functions bend downward like a frown, and then concave up function bend upward like a smile. Okay, so therefore again you will see that in this case, just like okay, then this is the graph of f line below. That means again, this is a concave down here. Okay, this one bend upward like a smile, then this is a concave up. Then okay, just like the example that we have for x squared, isn't it? Okay. Okay. Then let's look at it in detail then. Okay. So you will see that in this case, the function is increasing. This is also the function is increasing. But again, because this bend downward, okay, so therefore this is the concave down. The function is decreasing, but this is also the concave down. Okay. This one right here is increasing, but bend upward, right? So it's concave up. This one is decreasing, but again, it's bend upward. So it's still a concave up. Then. Or if you look at the slope, okay, then the slope from here to here and the slope from here to here, okay, you will see that the slope, maybe we could say that this is 3, this is about 1. Okay, the rate of change is decreasing. Okay, and how about this one? Okay, so to this one, we have this, the slope is -1, and then okay, to this one, the slope is about, again, we go down by 3 units, 1 by 1, so it's about -3. Okay, so we're changing from -1 to -3. Again, the rate of change is decreasing, right? Okay. How about this one? Okay, so okay. So this one is about 1, and then from here to here, then of course we see that the rate of change is increasing. Okay, so therefore it's concave up. And same thing here. This one, the slope is about -3. This one, it is about -1. Okay, so again, the rate of change is increasing. Okay. We could also using a tangent line to help us to identify the concavity as well. Okay. If the graph F lie below all of its tangent line, you see the tangent line is here, here. Okay. On an interval I, then it is called concave down. On the other hand, if the graph of F lie above, okay, all of its tangent line on the interval I, then in this case right here, we have concave up then. Okay. Then now let us try to see how we locate the inflection point. Okay, or sometimes we call it a point of inflection then. Okay. So remember, how do we do this? Okay, we would like to find a point where the function is changing from concave up to concave down, or concave up to concave down, concave down to concave up, right? So this point right here is the inflection point. Okay. So in this case right here, if we have the function f, how do we actually estimate, okay, the point of inflections? Now this actually is always my first approach. Okay, maybe I call it the step, always the first approach. Okay, if you have the function f, I would like to find the local maximum and the local minimum, and the point of inflection basically is somewhere in between. Okay, the local maximum and minimum, a point on the curve. Okay, somewhere in between. Is also find somewhere that is easier to read. Okay, Then, of course, in this case right here, we found out that the inflection point, okay, is the locations 1, 1. Okay, now remember, this is the point that we have. Okay? And then now I would like to find the interval that is where the function is concave up or concave down. Okay, so in this case, we would like to see that, oh, from here to here. Okay, maybe I consider that the function basically is go to negative infinity, okay, of its domain. Okay. So then in this case, you will see that what happened. The concave, this portion of the graph is concave down. Okay, so we could say that x is less than 1. Okay, but of course we would like to use the maybe using the interval rotations. So I could use a negative infinity to 1. Okay. Then how about this interval right here must not, it actually is a concave up then. Okay, so it is from 1 to infinity. Okay, so therefore again, when I try to locate the inflection point, what I need to do, basically I need to again locate the point of inflection first, and after this then we will be able to work it out. Okay, the concavity, find the interval of the concave up and concave down then. Okay. Okay, so now then let's talk about the concavity test. Okay, it said that if f double prime of x is greater than 0 for all x in I, then the graph of f is concave up. Okay, just like what we talk about this, f double prime is positive, right? Then the function is concave up. If f double prime of x is less than 0 for all x in I, then the function f is concave down on I. Then now, how do we actually find the point of inflection now? In this case right here, if f is continuous at P and f change concavity at P, the point P, f of P is an inflection point of f, okay? Then, in this case, the idea is first, suppose that f double prime of P is equal to 0, okay? And then now, if f double prime changing from positive to negative, okay, at P, then this point will be point of inflections. In other words, to the f functions, it's changing from concave up to concave down. Okay. On the other hand, if f double prime again, okay, changing from negative to positive, then to the f functions, changing from concave down to concave up, of course, this P right here is the point of inflection then. Okay. On the other hand, what if it didn't change the sign? Okay. If it didn't change the sign, that means this one thing about this is maybe this is a concave down and then this is a concave down, right? So therefore, in this case, it's not a point inflections. And maybe this is a concave up and then do concave up, right? So then again, this is not a point inflection then. Okay. So then what is another, again, the second derivative test now. Suppose that f double prime is continuous near C. Okay. And if f prime of C equal to 0. Okay. Now remember these tell me again f prime of C equal to 0, which is C is the critical numbers. Okay. That means in this case right here, if it is a critical number, meaning it could be the local maximum or minimum then. Okay. And if f double prime of c is greater than 0, okay. Remember, f double prime of c greater than 0, meaning we have a concave up. This one, we have a concave up, and then c is a critical numbers. Of course, in this case, we have f has a local minimum as c. Okay. On the other hand, if f double prime of c is less than 0, meaning the function basically is concave down, right? And then because c is a critical numbers, so that means f has a local maximum as c then. Okay. Okay. Notice f double prime of z equal to 0, then the test is inconclusive. It may be a point of inflections, like the function f of x equal to x to the power 3. Okay. So again, we know that the graph, maybe let us try to see what is going on here. Okay. So I have f of x equal to x to the power 3. Then now, if I want to find critical numbers, okay, then I need to find f prime of x equal to 3x squared. And then I set this equal to 0. Okay. So when I solve it, then of course I find that x equal to 0, right? Then now, f double prime of x, it will be 6x. And now you will see that f double prime of 0 is equal to 0. Okay. And in this case, then what do you have here? We have, okay, this is f of x equal to x to the power 3. Then do you see that x equal to 0 is a critical numbers? Okay. However, f double prime of 0 is equal to 0. So this point right here, again, is not the local max or min. So that's why we say that if f double prime of c equal to 0, then this second derivative test will not give you any result. Okay, it's inconclusive. We don't know what it is. Okay, then probably we need to work with this one right here then, right? Okay. And now, again, this number 4 is, again, we would like to, okay, get it from f prime, okay, and then we would like to, again, try to graph the f functions, okay. Then let's see how do we actually work it out this problem, okay. Basically, what I will do is I will, okay, follow kind of like the procedure that we have it when we work with number 2, and I will add some more informations, okay, because this f prime right here is a bit more complicated than the function that we have on this problem number 2 then, okay. Then now let's try to work it out this problem, okay. Now first of all, maybe let us determine that the domain of f, okay, maybe I make it between 0 and 9, okay, so just like this, okay. Then now you should be able to work on 4a, b, right? Because again, just use the technique that you have learned in problem number 2 here, okay? So try to see if you could work with to find out the interval of the function f where the function increasing or decreasing, and then determine the local maximum and the minimum then. Okay, so let's see how we work it out. Then, again, the first step is I would like to find the critical numbers. Okay. That means in this case, I would like to find f prime of x equal to 0. Okay. Now, in other words, meaning we are looking for find the x-intercept, right, of the f prime function. Okay. Then, in this case, I found out that x is equal to 1, 6, and 8. Okay. And second, I would like to create a side charge for f prime. Remember what we need. We need to put down, okay, 1, 6, and 8, okay, on this f prime. Nothing else, okay. And now we are looking for, okay, so between 0 and 1, the function is below the x-axis, so therefore it is negative. And then between 1 and 6, the function is about the x-axis, is positive. Between 6 and 8 is negative, and from 8 to 9 is positive. So again, basically we are looking for if the function f prime is below the x-axis or above the x-axis then. And now, number 3, okay, we are going to, again, work with that f function now, right? From f prime to f. Okay. So again, we would like to label out the 1, 6, and 8. So then negative, for f, it will be decreasing. And positive of f prime, increasing, decreasing, and increasing then. Okay. Then, of course, from decreasing to increasing, then we know that this is the minimum, increasing to decreasing, maximum. Okay. Ooh. Then now I will be able to answer my question for A and B now. Okay. So decreasing, it is from 0 to 1, union with 6 to 8. Increasing 1 to 6, union with 8 to 9. Okay. So again, because I assume that the domain is between 0 and 9, okay, then I will have the local max at x equal to 6, local min at x equal to 1 and 8 then. Okay. Then now we are going to add more information to the graph now, which is the concavity now. Okay. So I would like to find out that on what interval of f concave down or concave up or concave down word then. Okay. So remember when we talk about the concavity, we need to work with the second derivative, right? Okay. So then let's see. Okay. So again, how do we actually work with again the second derivative? Okay. Now remember, how do we get the second derivative? is we take the derivative of f prime, then this becomes the second derivative, okay? So what I'm going to do here is I would like to take the derivative, okay, of the f prime functions to get the second derivative. How do we actually work it out? Okay. So for the problem C and D, this is okay, this is how we work it out. First, I would like to locate the local maximum and minimum, okay, of f prime which is f double prime of x equal to 0 then. Okay. Then in this case, you will see that is when x equal to 2, 3, 5, and 7. So x equal to 2, 3, 5, and 7. Okay. Then second, looking for the increasing or decreasing of f prime. So then now 2, 3, 5, and 7. Okay. Then you will see that to this graph, okay, the function is increasing and then decreasing, increasing, decreasing, and then from 7 to 9 is increasing. Okay. And now, how is it translate to f double prime? Okay. So again, I still need to write down 2, 3, 5, and 7. Okay. Then remember, f prime increasing, meaning to f double prime is positive. F prime decreasing, okay, decreasing of f prime, meaning to f double prime is negative. Okay. And now, I know it's a lot of step, huh? I would like to work with the f function now. Okay, so again, we have 2, 3, 5, and 7. Remember, positive of f double prime to the f functions is concave up. Negative of f double prime to f functions is concave down. Okay. Then changing from concave up to concave down, then 2 will be the inflection point. From concave down to concave up, right, is also the inflection point. Okay. And now we could actually answer our questions for C and D now. Okay. So we're looking for concave up, then this interval is between 0 and 2, union with 3 to 5, union with 7 to 9. And then concave down in between 2 and 3, union with 5 to 7. Then. Okay. Then, of course, the x coordinate, right, of the point inflections is x equal to 2, 3, 5, and 7. Okay. Again, which is the local maximum and minimum of f prime. And then now, what we need to do is we would like to again sketch the function f now. Okay, so just like the previous problem, then first again I would like to have the coordinate system. Then this is x, this is y, 0. Okay. And remember, first, we need to work with the critical numbers. So it's 1, 6, and 8. Okay. So we draw a dashed line, vertical line, over x equal to 1, x equal to 6, and then 8. Then okay. And then we work with the increasing and decreasing. Okay. So then we have it first, it is decreasing between 0 and 1, and then increasing from 1 to 6. Okay. And then decreasing again from 6 to 8. Just use a straight line, okay? And then from 8 to 9 is increasing, okay? And now, before we sketch the functions, I would like to add the critical numbers, okay? Actually, is the inflection point now, okay? So when x is equal to 2, when x equal to 3, x equal to 5, x equal to 7, okay? And then now, just keep that in mind. First, I need to have the local minimum at x equal to 1, local maximum at x equal to 6, and minimum at x equal to 8, right? Okay. Then now, between 0 and 2, I have this is concave up. Okay. And then now, between 2 and 3 is concave down. And then from 3 to 5 is concave up. And then from 5 to 7 is concave down. And then from 7 to 9 is a concave up. Okay. So then this will be my f function. Okay. This is again how we using the f prime and f double prime to help us to sketch the function f then. Okay.